Hi and welcome to my video on determining stationary points using calculus. So I've got an example here. I've chosen a polynomial. You might be at the stage where you're using other functions, but I'm just doing a teaching, keeping it simple. This is about the stationary points in the process. I've also drawn this graph here. It's pretty rough, I'll be honest, but it's got the key points there and the key features, okay? So here it is. This is a cubic, and there's a sketch. We want to find the stationary points. But first of all, what is a stationary point? A stationary point is this point here and this point here. Those points where the gradient is 0. Because that's the point where it's moving up, the function's moving up, and then just for an instant, it's not moving up or down. So it's stationary. And if you put this in context, particularly a kinematics context, that's what a stationary point will be about. So that's the first thing. Now we're going to talk about how to find these stationary points using calculus. Well, I mentioned a word earlier. I said, this is where the gradient is 0. This is where the gradient is 0. So we need to find where the gradient is 0. So what we're going to do is get this function up here, and we're going to get the gradient function, because remember, when we derive, that gives us the gradient function. It tells us what the gradient is for any x value. So I'm going to derive this function, and again, I hope that it's a fairly simple derivative for you. But I bring the 3 down. 3 times 2 is 6. I get 6x, and the 3 decreases to 2 because it's a polynomial. And then I do the same thing here, but this time I get 6x, and then minus 12x becomes minus 12, and of course this plus 4 in the end just becomes 0. So go back and have a look at your polynomial derivatives if that's a problem. But now I've got this, and I'm going to say, well, let's let dy dx equals 0, so we can find our x values that allow dy dx to be 0. So I get this, 0 equals 6x squared minus 6x minus 12. I'm going to skip some of the maths. I'm going to be a little bit quick on this, but try it out yourself, see what happens. First thing I say I can do is divide by 6. That's going to make my life a bit easier. And I get this, 0 equals x squared minus x minus 2. That took me a moment. And then I'm going to factorise this and solve, and I can factorise it. You can't always factorise quadratics, but in this case I get x minus 2, x plus 1. And of course when I solve that, I get x is equal to positive 2 or negative 1. So that tells me my stationary points exist here, and this has an x value of negative 1, and here, and this has an x value of 2. And that makes sense, it suits my graph. So if you sketch this, this should make sense with the result you get there. But there's a couple of things we have to do because we're determining the stationary points. So the first extra thing we have to do is we have to find the equivalent y values. Because obviously we've got the x value, but we don't know the point, the coordinate. So just be wary of the wording of a question as to whether you need to find the coordinate or maybe just the x values, the stationary points. So I'm going to go through and find if x is 2, what does y equal? So at x equals 2, y equals, I'll skip some of the maths again, but it's 2x cubed, which x cubed is 8, so this is 16, minus 3 times x squared, which is 12, minus 12 times x, which is 24, so this is 2, and then plus 4, and that gives me negative 4, negative 28, plus 4 is negative 24. Oh, I've got that wrong. So negative 4 minus 24 is negative 20, so this is minus 16. There we go. And so our coordinate here is 2, negative 16, and I can mark that on our graph. 2, negative 16 is the coordinate. And then my second point is x equals negative 1, and I get y equals, notice here I know that should be a negative value, and that's what I was heading towards. And I'm going to do the same thing here. I'm expecting a positive value. And I know that the y-intercept here is 4 because it's there. So I'm expecting it to be a little bit bigger than 4. So I've got 2 times negative 1 cubed is negative 1. So that gives me negative 2. Negative 1 squared is 1. So negative 3. Negative 12 times negative 1 is positive 12. And then plus 4. And so that gives me 11. So it may be a little bit higher than I was expecting, but like I said, my graph is not perfectly accurate. This leads to this coordinate, negative 1, 11, and so I can put that up here. So there's my two stationary points. The last thing I have to do, and you'll do this with any function group, is I need to check the nature of the stationary points. So what I'm going to do here is I'm going to do this using a second derivative test, but I'm going to talk about something called the gradient table test as well. It will introduce it to you, and then you should learn more about it in the class. So let's do this one, and I'll move back to my green pen here, and we're going to do the second derivative test. So I'll just write down a title, and I'm hoping that I won't run out of space down here, but it's not too hard to do. So what's happening is first I need to get the second derivative, which has this notation: d squared y dx squared, or y double dash if you're using that notation. So d squared y dx squared, and in this case the second derivative of this function, so if I derive it again, I get 12x minus 6. Now I'm going to check that second derivative at x equals 2 d squared y dx squared equals 12 times 2 minus 6, which is 18, and at x equals negative 1 d squared y dx squared equals 12 times negative 1 minus 6, which is negative 18. Now the 18 itself is not important to me. It does measure something. It measures the rate of change, and that 18 is quite a big number, so it's moving pretty quick. But it's not actually important to me for this question. What's happening here is the first one, at x equals 2, I'm told that the squared y dx squared is positive. So that means that the gradient is changing in a positive fashion. So whatever happening, if the gradient's here, it's now increasing. Now I'm a bit scared this is going to look the wrong way around on the video. So I'm going to draw it, okay? And I'll pop it in here in yellow. So if the gradient's positive, like that, so yeah, it is this way, then it's increasing, which means that if it's 18, the next second it's like that, and then it's like this, and then it's like this. So let's take it actually from a negative gradient. A negative gradient increasing will start to curve around and do that. An increasing gradient over time leads to a minimum. So this is a minimum. It's a low point, I suppose. So this is now called a minimum. And of course, a negative second derivative will look like this. It's going like that because the gradient starts positive, ends up at 0 at some point, and then becomes negative. So because it is a decreasing gradient, then over time it turns around and becomes quite negative, which means it actually represents a maximum. Now this is a little bit counterintuitive, but if you just remember it's counterintuitive, then that's alright. It makes sense, obviously mathematically it makes sense, but you kind of want the second derivative positive to be maximum and negative to be minimum. That's just not the case mathematically in this case. But there we have it. I've determined that that's a minimum. There's a point, that's the maximum. You do have to do this test, although logic would tell you that if this is higher than that, so how could this be a minimum and that be a maximum? It doesn't really make sense. But say, for example, you've got a quadratic or you've got another function. I'll give you an example. Another more complex function that has only one would be y equals x natural log of x. And if you haven't seen natural log, you'll be introduced that soon. But x natural log of x has one turning point. How do you know if it's a minimum or a maximum? The only other thing you can do is called a gradient table test. And these actually represent the gradient table test quite nicely. So I'll just... so what we have here is if it's a maximum, if you test the gradient at your x value, so at negative 1 here, then the gradient should be 0. If you then test it just below and just above, so let's say I test it at negative 2 and 0, negative 2 the gradient is positive, then it's 0, and then it's negative. And if it's positive, 0, negative, then that is a maximum. And equally down here, you test it at 2, test it at 1 and 3, negative, 0, positive, it's a minimum. So there you have it. Stationary points. It's as simple as get the original function, derive, let the derivative equal 0. You'll see this process a lot. Derive, let the derivative equal 0, solve to find how many x values this equals 0. Okay, it might be 1, might be 2, might be 100. If it's a periodic function, for example, there's going to be an infinite number. So there's my answer to that. That will give you each turning point. Then You need to find your equivalent y values, maybe, depending on the question, and you should always do a second derivative test or a gradient table test to finalise which ones are minimums and which ones are maximums. So sorry, this has been a bit of a long video, but it's a really important process, and typically in an exam situation, pretty easy marks if you understand and you can apply the process effectively. Thanks for watching.